Hello and welcome to our first video in a series of videos where we go through various organic chemistry peer-reviewed literature articles. And what I do is pick out a few reactions that are relevant to undergraduate organic chemistry courses. And what that does is it allows us to essentially use real life reactions which relate to things that are actually relevant to the world, like medicine, etc. And we can then relate that to the abstract concepts presented in class, and we can go through the reactions in detail. And hopefully we can get a little bit more out of it than just what we would normally do sitting in class, going through organic chemistry reactions and mechanisms on paper and not understanding what the purpose of those reactions are, and we're thinking, once I'm done with this class, that's the end of it, so I'm just going to get through now. But I'm here to show you that there's a lot more to this and that it actually applies to real life. So the publication I chose for the first video is a total synthesis and structural elucidation of Khafrefungin. And this is from Wakabayashi et al. From the University of Tokyo. And so in this publication, they do the total synthesis and structural elucidation of Khafrefungin, which is a novel antifungal agent isolated from a fermentation culture MF6020 by Merck Group in 1997. What they found is that the Khafrefungin has been shown to inhibit biosynthesis of IPC in various fungus, but when applied to mammals, it does not inhibit this biosynthetic process. Therefore, it could be a potential therapeutic agent for humans or for animals, mammals, and it doesn't disrupt this process. So it's only selective to fungus. What they do in this publication is they create these sort of mimics of Khafrefungin. So there's compound here and compound 2. Now, the reason that they are creating these mimics is because the Khafrefungin, the natural product, is very complicated and large, and it has these stereocenters here. We could point out several stereocenters. They give rise to 8 potential stereoisomers. Now, in the natural product, they don't know exactly what mixture and percentage of stereoisomers that they have that they made in their fermentation culture. So to keep it short and make this a little bit easier to elucidate the structure, they make these mimics which have similar stereochemistry, stereochemical centers that can be altered. And when they subject this to NMR analysis, they can get a clear NMR signal, which corresponds to the stereo center in different ways. So then they can pinpoint, okay, if we have a certain stereochemistry, we get an NMR signal that looks like so and so. If we compare that to our natural product, we can determine which stereo center we have in our natural product. So they synthesize these more simple to make mimic compounds to elucidate the structure of Khafrefungin, which is a more complex molecule. Now, going through this publication, the scope of this is more purely synthetic and then structural elucidation, which is great for organic chemistry students as examples. And the scheme that I picked out starts with this structure right here, compound 5. And because it's a more simple reaction scheme that we can go through, and all the reactions pertain to things that you will see in undergraduate organic chemistry, particularly organic chemistry 2. So keep this in mind. This is the starting material 5. And if we go down, we see this synthetic pathway continue. So starting from 5, the overall scheme is to make 7B. And this allows us to use this compound, subject it to NMR analysis, and then determine the stereocenters and use these essentially as controls to figure out the exact structure of our Khafrefungin. So to go into more detail on the reaction scheme, in reaction A, we do a Wittig reaction using this compound right here, which is taught in most or all organic chemistry courses. Very useful reaction. In reaction B, they go from this compound, our ester, to an alcohol, and they use a reduction with diol. In dichloromethane, negative 78 degrees Celsius, very standard conditions. So for reaction C, they use a sharpless epoxidation. So they use TBHP, titanium isopropoxide, and D-tartaric acid diethyl ester. Now, this might be a little bit beyond the scope of undergraduate organic chemistry, but it's a very cool reaction because it's very stereoselective, and it allows us to add an epoxide in a very particular way that we can control instead of creating multiple stereoisomers. We can just create the one that we want by changing the type of tartaric acid diethyl ester that we put into the reaction. So that essentially acts to direct where we add our epoxide, which phase we add the epoxide to. Finally, we have reaction D, in which we just do an epoxide opening reaction with methyl lithium copper iodide. So this is Gilman conditions, and we form a Gilman reagent, and then we add the CH3 group to its position, opening our epoxide, and we get a diol. So that's about the scope that we're going to go into for the sake of covering what is commonly seen in undergraduate organic chemistry. Now, what I'm going to do is I'm going to switch over to ChemDraw. And so just a little background. ChemDraw is what I use for a lot of tutoring. It's really great because it's very nice and clean, and it's something that students can take home with them after our session. So generally what I do is I ask students to send me the material ahead of time, whether that be homework that they want to go through or any class material or just cover lectures, whatever they want to do. And then I can, if they send it to me in advance, what I can do is I can set up reaction schemes. I can set up reaction mechanisms, but without the arrows, for example, and then the student and I can walk through the reaction and draw the arrows together, and it really makes things efficient, and it makes things go along really fast, and we can get a lot done in a session. Afterwards, I can send this to the student in a whatever document form they want, a JPEG, GIF, whatever, and they can have a electronic or even printed copy of what we covered during our session. And a lot of this organic chemistry stuff is not something that you can understand right away. A lot of times I like to say you have to sleep on it because it doesn't make sense right away. It's complicated, and you have to look at it a few times before you get the gist of it. For most students in organic chemistry, it's not something that's just immediately apparent. Back to the reactions in this publication. So as you can see, I've drawn out all the reaction schemes that I briefly talked about in the publication. So we have compound 5. We go through a Wittig, we do a reduction with diol, we do our sharpless epoxidation, and then we do our Gilman reaction with our epoxide to make our diol. And let's go into the first reaction. So the first reaction is a Wittig reaction. And if you're watching this video, I assume you know a bit about the Wittig reaction because it's very common and very useful in organic chemistry courses, particularly organic chemistry 2. So let's walk through the mechanism for this. So we use an ylid in Wittig reactions, which is by definition essentially a negatively charged carbon, which is bonded to a positively charged heteroatom, and there's a separation of charges. Now you could see your ylid written in this form with the double bond, but what I'm doing here in this first step is pushing the electrons to the carbon, essentially making it a carbanion, just to show us where our nucleophilic center is, and that would be right here. So this helps us to identify the nucleophile, and then we can use our nucleophile to react it with our electrophile, and it makes things a little bit easier when you walk through organic chemistry systematically like that. So I do your separation of charges first. Now we go to this step. We have our nucleophile right here. We push the electrons to this carbonyl center, which is our electrophilic center, and then push the double bond oxygens, carbon oxygen electrons to the oxygen. Our next intermediate is our negatively charged oxygen. The lone pair on the negatively charged oxygen that we generated attacks that positively charged phosphorus, and we make this weird square intermediate that we see with Wittig reactions. And so what we do here is we want to create a double bond ultimately in our product, and that would be with this bond right here. So we're going to break this carbon to phosphorus bond by pushing arrows from that bond to this carbon to carbon bond. And then we want to also break the oxygen from our carbon, and we break that bond and we form a double bond between the oxygen and the phosphorus. And as you see from that strange mechanism, we create our product with our double bond right here. And we make triphenylphosphine oxide, and we can easily separate that from our reaction during our workup. So that is how we make product 19 using a Wittig reaction. Next, in this reaction sequence, we are going to reduce our ester from compound 19 to compound 20. They use diol, diisobutyl aluminum hydride. Now, this is commonly encountered in organic chemistry as a reducing reagent, which only reduces one step. So a lot of students will see this where a professor will give them like an acyl chloride, for example, and under conditions where they're subjected to diol reduction, your acyl chloride will only proceed to an aldehyde and the reaction stops. It doesn't go all the way to an alcohol. So it's usually just shown or presented to students in organic chemistry as a strong reducing agent, which only can donate one hydride to your substrate and perform one reduction step. So here's the mechanism. And what we'll see in this mechanism is we sort of do two subsequent reductions, assuming we have extra equivalents of diol, and we're essentially going to repeat that one hydride addition reduction two separate times with two equivalents of diol. So first step in the mechanism is we take our lone pair of electrons from our oxygen, attack that aluminum of our diol. We form a coordination between the oxygen and aluminum. And in this step, we take the aluminum to hydrogen or hydride bond, and we take the electrons from that hydride and we push that to the carbonyl carbon, which is our electrophilic center, and we add a hydride to that carbonyl carbon. And subsequently, we push the electrons between our carbon and our oxygen to the positively charged oxygen, alleviating the positive charge. Finally, after we see we've added this hydrogen here from our diol H, we break the oxygen to aluminum coordination bond, and we form a double bond between our oxygen and our carbon right here to regenerate our carbonyl. And we kick off our OET or ethoxide. Our next step, we essentially repeat the reaction, like I said, and we come back in with our aldehyde now instead of ester, attack our aluminum center. We form our aluminum oxygen coordination. Again, our hydride comes in, attacks our carbonyl carbon. We swing the carbon to oxygen double bond electrons to the oxygen to alleviate that positive charge. And we get to this intermediate, tetrahedral intermediate, essentially where we've added two hydrogens and we have our oxygen to aluminum coordinated. So we just quench this reaction or subject it to aqueous conditions, and it cleaves off that aluminum oxygen bond, and we generate our alcohol now from our ester. So we have product 20. So that's our diol reduction. Next, in our third reaction sequence, we have our compound we just made, compound 20, and we react this with TBHP, titanium isopropyl oxide, and D-tartaric acid diethyl ester in dichloromethane at -15 degrees C. And as you can see, we make an epoxide. So this is a very interesting reaction beyond the scope of undergraduate organic chemistry courses, but very interesting and worth talking about nonetheless. So this is essentially a catalytic mechanism with our titanium species, and we're going to walk through this mechanism. It's not that bad. It looks scary, but it's not very scary. It's actually very cool. So we start with our titanium isopropyl oxide. I highlighted in green the two groups that we lose first. So you can see right here, when we lose this, I can notate it as this isopropyl alcohol group, and it keeps things straightforward and simple. So you can follow along where everything is going. So I left the stereochemistry out of the diethyl tartrate, just to make it more simple, because it might be beyond the scope of undergraduate organic chemistry courses. So essentially we introduce our diethyl tartrate, whatever stereochemical species we want to use, depending on how we want to make our epoxide, which phase we want to add it to. So that's added into the reaction. We lose two of these isopropyl groups, and now we coordinate this diethyl tartrate to our titanium. And the stereochemistry of these bonds right here can help us later in the reaction force geometrical changes which allow us to use our reagent to add to a certain phase or another phase by choosing this diethyl tartrate. So the diethyl tartrate, the stereochemistry that we choose, is very important to the stereoselectivity of this reaction. Next step, we add our TBHP, tert-butyl hydroperoxide. And again, we kick off this isopropyl alcohol group, lose it as an isopropyl alcohol group highlighted in green, and we are left with then this intermediate in our catalytic process. So as you can see, we have our peroxide here, which is essentially our reagent that is bound to our titanium, and this, we'll see in the next step, allows us to direct the reaction. So as you could probably guess, I highlighted this isopropyl group in green, and when we substitute in our substrate, which has an alcohol, and if you notice all these coordinations to our titanium are groups with an O, oxygen, that are generally alcohols. So we can brilliantly add in our substrate, and we can coordinate that oxygen to the titanium center. So when we do that, you can see right here, the most important step is we have our reagent right next to our substrate, which is great. And then it's in a certain conformation where we can add in a specific way to get a very stereoselective product. So we can make the exact product we want and dictate where the epoxide goes. So the first step of this mechanism is double bond goes to this oxygen. We break the titanium to oxygen bond, and the electrons go to the second oxygen, and then the oxygen-oxygen bond breaks going to the other side of our double bond. And in this process, we form our epoxide. This is a pretty general mechanism for epoxidation and other reactions like halogenation is very similar. So we generated our epoxide. This is essentially our finished substrate coordinated to our titanium catalytic species. Now, as you guessed, again, we put in one of the isopropyl alcohol groups that we kicked off at the beginning. And what that does is that kicks off our product. And so we now have our product 21 right here. But what I'm going to do is finish this catalytic cycle. So we can throw in another equivalent, which is just floating around a solution. Since we kicked it off our original titanium isopropyl oxide, this isopropyl alcohol group can come in to our species, and then it kicks off our tert-butyl alcohol, which was the essentially depleted reactant that we put in form of the hydroperoxide form of it. And then we regenerate this species, one of our catalytic intermediates. So our titanium still coordinated to our stereoselective agent and the two original ligands that we had on it, the isopropoxide groups. And this is essentially our entire mechanism for this reaction. Again, I left the stereochemistry out to keep it simple because it's fairly long for the scope of undergraduate organic chemistry, but we have our compound 21. Moving on, we have our compound 21 we just generated, and we're reacting it with methyl lithium copper iodide ether at 0 degrees Celsius, and we make 7B. As you can see, we are opening our epoxide, and we're adding a methyl group here. And brilliantly, they use a Gilman reagent. So we add in methyl lithium copper iodide, and we create the Gilman reagent. So that is expressed down here. So addition of these reagents to make our Gilman reagent. And so our Gilman reagent, our copper to alkyl group bond breaks, and we use those electrons, we push those electrons to the least hindered position of our epoxide. And this is very common under basic conditions. Under basic conditions, epoxides are opened by addition of your nucleophile to the least hindered side of the epoxide, or least substituted side of the epoxide. Under acidic conditions, we add to the more substituted or more hindered side of the epoxide. Obviously, this is a fairly strong base, so we're going to add to the least substituted or least hindered side of our epoxide, which is at this carbon. And we retain the stereochemistry of the other side of the epoxide, in which we are not adding our nucleophile. So our nucleophile comes in from the back, and we add in an anti fashion. So our next intermediate is this intermediate with a negatively charged oxygen, and we can see we have our CH3 group added anti. And finally, we subject this to a workup, possibly acidic conditions, just workup conditions, and we can protonate that alkoxide, making our final alcohol. And this is our final product, 7B, which we can then use to elucidate the structure of our natural product. So thank you everyone for checking out this video. Please like, subscribe, comment, and I'd really like suggestions from anyone who has any cool ideas about materials or peer-reviewed literature that they would like to cover or have me cover, go through the mechanisms. That'd be really great. If anyone is curious about any organic chemistry stuff, please feel free to message me or comment, and you can email me at talontutors@gmail.com, and have a great day.